Educational videos by MMS programs. Chapter 2, Design Concepts of a Singly Reinforced Rectangular Section Flexure Member. Part 1. This is a slab supported on two edges. This is called as one-way slab. The spanning of the slab is in this direction. The deflection of the slab will be something like this. The top fibers will be in compression and the bottom fibers will be under tension. We know concrete is weak in tension, so we provide structural steel or reinforcement in the tensile zone to take the tension. This is a two-way slab. So a two-way slab deflects like this. It takes a saucer shape when loaded from top. Okay. So in case of two-way slab, you have to provide main reinforcement in both the direction. This is again a slab supported on all the four sides. Ly is the longer span, Lx is the shorter span. When the aspect ratio, that is Ly by Lx, is found to be greater than 2, then it has to be designed as a one-way slab, because in that case, the curvature of deflection in the longer side is very mild and can be neglected. So you can take this slab as spanning in this direction with main reinforcement in this direction, and you can provide nominal reinforcement in this direction, that is to take care of temperature and shrinkage effect. Similarly, when the aspect ratio Ly by Lx is less than equal to 2, then you have to design the slab as a two-way slab. In that case, you have to provide main steel in both the directions. This is a simply supported beam. When loaded from top, it will deflect like this. The top fibers will be under compression, bottom fibers will be under tension. As we know, concrete is weak in tension, so we provide reinforcement in tension zone. So we provide AST in tensile zone. This is a simply supported beam. Okay. So take care. This will take the tension. Okay. And these top bars are known as hanger bars. They are not considered in design. They are provided just to fix the stirrups in location. Say suppose it is a cantilever, then cantilever will deflect like this. The top fiber will be under tension and bottom fiber will be under compression. So the steel has to provide, the tensile steel has to be provided at top. Okay. Two kinds of problem in case of RCC design, that is analysis and design. In this chapter, we will study regarding the analysis. Analysis of a flexure member section. In this case, all the properties of the section are known to us. Cross section of the member, that is B and T. Concrete grade, that is it is whether M20 or 25. Grade of steel, that is whether it is Fe415 or Fe500. Area of steel, that is tensile steel AST. Accordingly, we can find the corresponding stress in the section and the ultimate moment of resistance, that is MUR is equal to C into lever arm, or MUR is equal to T into lever arm, right? So once you know all the properties of the section, including the size, the grade of steel, concrete and area of steel, then you can easily find C and T. C is compression force due to the design stress strain diagram of concrete, and T is the force that is taken by the tensile steel. Okay, once you know C, once you know T, once you know D, you can find Z. Z is the lever arm, that is D minus 0.416 x. This we'll see in detail as we move forward. So that is how we can find the moment of resistance very easily. C into Z will give you the moment of resistance, or T into Z will give you the moment of resistance. Okay, so for a known properties of a section, you can have unique solution, that is you can have one value of C, one value of T and one value of MUR. Okay, so that is what we do in case of analysis of a section. Design of a flexure member section. In this case, the moment and shear force are obtained from the structural design, and it is required to select appropriate grade of concrete, grade of steel to arrive at the member cross section dimensions and the area of the steel required to resist the design moment. Okay, design bending moment and the shear force, right? So this is the moment which we get from the structural analysis of a frame or of a 3D frame or 2D frame, okay, and for which we have to design the section, and the section, the grade of the concrete, grade of the steel, B, D, and the area of steel are to be so selected that the moment of resistance, that is C into Z or T into Z, is found to be greater than the design moment, so that the section can resist the design moment, right? So there can be various number of solutions as according to the need of the structural designer. So some structural designer may take B as 250, some may take it as 300. So accordingly, the section size may vary as according to the need of the structural designer. The grade of the concrete may vary as according to the need of the structural designer. And so you can have a number of solutions for uh, resisting a design moment as according to the requirement of the structural designer. Assumptions for analysis in limit state of collapse. Please remember, we are at present discussing limit state of collapse, that is ultimate limit state, right, and not limit state of serviceability. So we will be following the rules and assumptions for limit state of collapse. Plane section normal to the beam axis remains plane after bending. Okay, so this is a beam uh, before bending. Okay, so this is the axis of the beam. So this is uh, plane section which is normal to the axis, right? This is plane section which is normal to the axis. Now after we load the beam will deflect, right? So this is how the axis is beam axis will also deflect, and still the no, plane section remains normal to the bending axis, right? So this is what is explained in this figure. Okay, this is before bending, this is after bending. But the assumption is that the section remains plane and normal to the beam axis in both the cases, right? Okay. The maximum strain in the outermost compressed face of the concrete shall be taken as 0.0035. It is assumed that the flexure member failure takes place due to crushing of concrete and not due to the yielding of steel. This is very important. The strain variation is assumed to be linear along the cross section. Okay, so this is before bending. This is the plane normal to the beam axis. After bending, so this plane is this. After bending, right? This plane still remains normal to the bending axis. So this is this, right? So this is our strain diagram, right? And the maximum strain that the concrete can take, or you can say the ultimate strain in the concrete, which we consider is 0.0035, after which the concrete starts crushing. Okay, and the code says that all the flexure member fails due to crushing of concrete and not due to the yielding of steel, right? Okay, the steel is assumed to yield at the yield strain, that is 0.002 plus 0.87 Fi by ES. So how do we get this? So we get this from the design curve for the steel, right? This is the design curve for Fe415. This is the design curve for Fe500. So this is our proof strain as we have understood in chapter 1, that is 0.002. This is the yield point for Fe415. This is the yield point for Fe500. So we want to find the yield strain for Fe415. So this is our yield strain, right? How do we get this? So we know we have to find the total strain. This is 0.002, and this we can find as 0.87 F5 divided by ES, right? Where 0.87 F5 is the design stress. Okay, this is design stress divided by ES. ES is the modulus of elasticity of steel. So that is how we get this distance. So this plus this, that is what we get this. So this is assumed to be the yield strain for the steel. Okay, that is what HY is equal to deformed bars, right? Okay. So as we have studied in chapter 1, the yield strain for deformed bar is taken as 0.002 plus 0.87 Fi by Es, and for mild steel the yield strain is taken as 0.87 Fi by Es. In case of mild steel, we know that it has a specific yield point, so the graph is something like this, right? Okay, in that case, this will be the yield strain simply. So in that case, you will not have any proof strain. So you will directly get 0.87 Fi by Es. Okay. Now, the next assumption is the design stress strain curve for concrete in flux and compression is suggested by the code as shown below. This is what we have studied in chapter 1. Okay. Now, the concrete for concrete, the partial safety factor to be taken is 1.5. For steel, the partial safety factor to be taken is 1.15. The tensile strength of the concrete is ignored in case of limit state of collapse for flexure. Okay. So say suppose this is a simply supported beam. Okay, in case of some simply supported beam, the concrete above the neutral axis is under compression and the concrete below the neutral axis will be under tension. So code says we are designing a crack section, and so the tensile strength of the concrete is neglected, and it is assumed that all the tension is taken by the steel alone. Okay, so this force T is due to the tension that is taken by the steel alone, which acts at the CG of the AST, right? And this is force C, right? That is due to the design stress strain curve of the concrete that will be taken by the concrete in compression. Okay. Okay. The yield strain in tension for reinforcement for the yield strain in tension reinforcement at the ultimate limit state method in the at the ultimate limit state method shall not be less than 0.002 plus 87 F5 by ES, regardless whether it is the cold work bars or you can say deformed bars with no specific yield point or mild steel with specific yield point for the convenience in design. Okay. So here we know this is the yield point, yield strain for uh, deformed bars. This is the yield strain for mild steel. But the code says that in both the cases you have to take this as the yield strain, whether it is a mild steel or it is a deformed bar. Okay, fine. So let us move forward. Cracking moment. Concrete is weak in tension. Okay, concrete is weak in taking tension. It is the moment due to which the outermost concrete fiber in tension zone reaches its maximum flexure tensile stress and gets cracked. Okay, so this is a simply supported beam. When it is loaded, it will deflect. The top fiber will be under compression. The bottom fiber will be under tension. When when the tension in the bottom fiber increases or is found to be more than the uh, permissible tensile stress, then the first crack will develop. Okay, so this is also known as modulus of rupture, that is FCR. According to IS 456 2000, the value of FCR is 0.07 under root FCK. So we can also find the cracking moment by using this formula. So MCR is the cracking moment and is equal to FCR into I gross divided by YT. I gross is the moment of inertia of the gross section and YT is the distance from the neutral axis to the outermost tensile fiber, right? Or outermost tension fiber, right? Okay. Concrete stress block in Flexure compression. Whether it is a case of balanced section, under reinforced section, or over reinforced section, the concrete design curve is the same as shown in figure below. Okay, so this is a design stress strain curve given in the code. So whether it is a under reinforced, over reinforced, or a balanced section, this design curve has to be used. Okay, that is what the code says. Okay. The ultimate failure in RC beam in Flexure occurs due to the crushing of concrete for all the three cases mentioned above. Okay. When the extreme compression fiber reaches the ultimate strain point 0.0035, okay, then you can say that the concrete will crush, right? So this is the design strength, you can say, design stress of concrete, that is maximum 0.447 FCK. It is assumed that when concrete reaches the strain point 0.0035, then it will start crushing, and the failure of the flexure member occurs due to the crushing of concrete, right? Now, below figure shows that how the value of the compressive force C can be computed. Okay, so this is force C. This is our design stress strain curve. So this can be divided into two parts, one rectangular part and another is parabolic part. This is C1, this is C2. When you add C1 plus C2, you get force C, right? So let's find C1 first. Okay, C1 is this portion, right? The area of this is 0.447 FCK into 3 by 7 XU. So the area of this portion is area of this portion, right, into B, right? That will give you C1. So that is what I have written over here. C2, it is a parabola. So it is area is 2 by 3 into 0.447 FCK into 4 by 7 XU. So that is the area of this portion, right? Into B will give you the C2. So that is C2, right? So when you add C1 plus C2, you get 0.362 FCK B into XU. So that is how you get C over here, right? Now, how to find that where this force C will fall? Simple. Take moments about the outermost face of the uh, uh, outermost face of the compression zone, right? So C1 into this distance plus C2 into this distance is equal to C into J. Say this is J, right? So that is what I have written over here. So solving this, we get this distance as 0.416 XU. Okay, this is XU, right? XU is the depth of the neutral axis, right? Simple. So that is how we get J is equal to 0.416 XU. Okay. Now how to find force T? T is a force that is equal to stress into area of tensile steel. Stress is Fy. Okay. Now, if it is an under reinforced or a balanced section, then we know that the steel yields, right? So Fy will be equal to the design stress that is equal to 0.87 Fy. But in case of over reinforced section, the steel does not yield. So the stress Fy will be less than 0.87 Fy. So if you are designing an over reinforced section, then in that case you will have to find the actual Fy. Okay, but in case of under reinforced and balanced section, you can take Fy is equal to 0.87 Fy. Okay, ultimate depth of neutral axis actual limit. Okay, so based on the assumption given above, the expression for the depth of the neutral axis at the ultimate limit state XU max, or also called as XU limit, can be easily obtained from the strain diagram as shown above using the principle of similar triangles. So this is the strain diagram, right? We know now from the assumptions above that the ultimate strain in concrete is 0.0035 and the ultimate strain in steel should be equal to or greater than 0.002 plus 0.87 Fy by ES. Okay, we know D, effective depth. Effective depth D is the distance from the top to the CG of the steel. Okay, so knowing all this, we can easily find XU. Okay, so we can find the ratio XU limit by D. Okay, So this is what we get from the principle of similar triangles. Put the value of ET over here and we get this, right? So knowing the value of Fy, okay, ES is the modulus of elasticity of steel, that is the value of ES. Okay, we can make a table easily, which is shown over here, which is also shown in the code. So XU limit by D ratio for Fe250 comes out to be 0.53. For Fe415 it is 0.48, and for Fe500 it is 0.46. Okay, so this is very important. You just can remember this. This will be very useful to find whether whether the section which we are considering is under reinforced or over reinforced, right? Behavior of beam in Flexure. As per assumptions above, the concrete in the tensile zone is ignored as in case as the section is assumed to be cracked in case of limit state of collapse. That is ultimate limit state. Depending upon the amount of reinforcement steel provided, there can be three types of sections. One is under reinforced section, another is balanced section, and the third one is the over reinforced section, right? So we'll try to understand what is under reinforced section. In an under-reinforced section for a given load, the tensile steel reaches the yield strain 0.002 plus 0.87 Fi by ES first, and then the concrete reaches the failure strain 0.0035, and as and when furthermore loads are applied. Okay, so in under reinforced section, the steel yields first, that is it reaches the yield strain first, then slowly as you increase the load, then the concrete reaches its ultimate strain, that is 0.0035, and then the crushing of concrete takes place and the failure takes place, right? This type of section under goes yielding of steel. uh, this type of section undergoes yielding of steel, giving warning in terms of excessive deflection before collapse. Such failure is called as tensile failure. In under reinforced section, the actual neutral axis is above axial limit. Okay, now x is the red line is of for that is actual limit for the balance section. Okay, and blue is the actual depth of the neutral axis, right? So over here the actual depth of the actual neutral axis falls above the balance section neutral axis. Okay, the failure occurs when the concrete reaches the ultimate strain 0.0035, and by that time the yield strain in steel will be more than 0.002 plus 0.87 Fi by ES. Okay. Now, in case of under reinforced section, how to find the depth of neutral axis XU? So from equilibrium, we know that force C is equal to force T. Okay, so this is force C, this is force T. So solving this equation, we get this like something like this, and you can everything is known, and you can find XU, right? So this is how you can find XU. Now, second is balance section, right? Okay, in a balanced section, the compression strain in the concrete reaches the failure strain 0.0035, and simultaneously the steel also reaches the yield strain equal to 0.002 plus 0.87 FMAS in bending. Okay, in this case, actual Na and the balanced Na are the same. Okay, they are the same, right? The failure occurs when the concrete reaches its ultimate strain 0.0035. Okay, over here to find the depth of balanced neutral axis, XU limit. Okay, again taking equilibrium, C is equal to T. This is C, this is T. So you can, this is how you can find the XU limit, right? Fine. Simple. This is the stress in steel which we are taking as 0.87 Fi because the steel has yielded. Okay, in case of under reinforced and balanced section. That is why we can directly take the stress in steel as 0.87 Fy, right? Okay, over reinforced section. In a C beam section, when the ultimate strain of concrete 0.0035 is reached earlier than the yield strain in steel 0.002 plus 0.87 Fi by Es, then such sections are called to be over-enforced. Such design sections are not recommended by the code as they undergo a sudden failure, you can say a brittle failure without warning, and such failures are also called as compression failure. In this case, this strain is reached first before the steel yields, okay, and your actual depth of neutral axis is greater than that of axial limit, okay. So this type of sections fail without any warning, which is not recommended. So over-info sections are not allowed to for the design purpose, right? But still, if you want to find the depth of neutral axis for a over-info section, then these are the steps. From equilibrium, we know C is equal to T. This is C, this is T. Over here, the stress in steel is taken as FST and not 0.87 F5 because the steel has not yielded. That is why your FST will be less than 0.87 F5 and you will have to find FST, right? So this is the formula for finding XU. But for finding XU, first you will have to find FST. So when the steel has not yielded, the true location of neutral axis is obtained by a trial and error method called as compatibility method. Okay. So these are the steps which you have to follow for finding the actual depth of neutral axis in case of over reinforced section. So first you have to assume any value of XU, that is depth of neutral axis. So from that, you know effective depth D, you know the strain in concrete, ultimate strain in concrete 0.0035, and you can find the strain in steel using this formula, right? Once you know the strain in steel using this formula, you can find the strain from this table. This is for Fe415, this is for Fe500. If your strain is 0.00144, the corresponding stress FST in the steel will be 288.8, okay? Or if it is in between this, then you cannot do the interpolation. So now you know FST, right? Once you know FST, again from equilibrium C is equal to T, this is C, this is T. Now you know FST, you can find XU, right? So this XU, which is obtained from this step, has to match with the XU assumed in step number 1, okay? If this does not match, then again you have to re-assume another value of XU, perform all the steps again and check whether this XU is found to be nearer to the assumed XU, okay? And if it is found nearer, then you can take that as your actual location of the neutral axis, okay? So this is a trial and method and it's a very lengthy purpose, but still nobody designs over info section, so there is nothing to worry about it, okay? Now important definition, factored moment mu, right? The moment expected at the beam section at the ultimate limit state due to the factored load is called the factored moment. For example, the factored moment for a simply supported beam at the midspan is WL square by 8, where W is the factored load in kilonewton per meter. That is, the dead load and live load is multiplied with a particular factor, right? That is your factored load, and the bending moment obtained due to the factored load is factored moment. Ultimate moment of resistance MUR, the moment carrying capacity of the reinforced section under the ultimate load is known as the ultimate moment of resistance. Okay, so for the ultimate load, you find the strain, you find the depth of neutral axis, you find C, you find T, and C into Z or T into Z will give you the ultimate moment of resistance, right? Lever arm Z is taken as, we know, we have just studied that C falls at a distance 0.416 XU. So this lever arm will be D. This is D. So this is D. D minus 0.416 XU. So that is your lever arm. So T into Z or C into Z or T into Z will give you MUR, right? For the section to undergo a tensile failure, that is under imposed section, MUR has to be greater than your MU. MU is the factored moment, design moment. MUR is the ultimate moment of resistance. Okay. limiting moment of resistance. It is obtained, it is defined as the ultimate bending moment carrying capacity of a balanced section under the uh, ultimate loads corresponding to condition xu is equal to xu limit. In case of balance section, we have studied that the actual Na is the same as the balance section Na, that is xu is equal to xu limit, right? So mu limit is equal to c into z, and mu limit, this is c and this is z. We just studied how to find z. Okay, so this can be written in this form, and this k, the values of non-dimensional parameters k for different grade of steel are shown in the table below. This is the table given in the code, okay, which you can remember. Okay, so for Fe250, value of k is 0.149. For Fe415, value of k is 0.138. For Fe500, the value of k is 0.133. Okay, so now we come to limiting percentage tensile steel PT limit. Okay, when xu is equal to xu limit and mu is equal to mu limit, that is the balance section. Okay, there is a limiting percentage of tensile steel PT limit. PT limit can be found from this formula: 100 into AST limit divided by BD. AST limit is the steel tensile steel required for the balance section. B is the width of the beam. D is the effective depth of the beam. Right? Fine. So this figure is very familiar to us now. Okay. Okay. So we can take from the equilibrium of tensile and compression forces. That is, we know C is equal to T. C is equal to T. This is C. This is T. Okay. This is for balance section. Okay. XU limit and AST limit. Where AST limit is the area of tensile reinforcement, right? So from this we get xu limit is equal to 0.81 Fi AST limit divided by 0.36 FCKB, right? Now we can replace AST as PT limit BD from by 100. From here we get this, okay, right? So put the value of AST limit over here. So this formula turns to be this, and solving further we get this, right? So once we know FCK and we know Fy, then for balance section, this is the table given below. Table below shows the value of PT limit for singly reinforced balance section of rectangular beam for various grade of steel and concrete. Okay, for example, if you are using M20 grade concrete and your Fe and you are using Fe250, then PT limit will be 1.77. For Fe4 415 it will be 0.96. For Fe 500 it will be 0.76. So once you know PT limit, you can put the value of PT limit over here and you can find the AST limit. Okay, so PT limit, AST limit are very important factors, because for designing an under reinforced section, so whatever steel you get after design, when you check that your AST limit is found to be less than when your actual AST is found to be less than AST limit, then your section can be considered as under reinforced, right? So PT limit and AST limit and XU limit, this all are the benchmark. Okay, you can say from which we can decide whether our section is under reinforced or over reinforced, right? Important note, by doing the analysis of the section, we see in the graph below that the gain in MUR with the increase in PT uh, follows nearly a linear relationship up to balance section, right? So this is I've done one analysis example. Okay, so D1 is the effective cover, B is the width of the beam, D is the depth of the beam, F5 FCK. So by varying by varying percentage of steel, you can get unique moment of resistance and a unique depth of neutral axis. Okay, so in this graph we can see this green graph represents the under reinforced section. This section represents the balance section. The details of balance sections is shown over here. This is found by this formulas as we have shown over here. Okay, that is this is PT limit. This is how we found the PT limit. Then this is how we found XU limit. We also studied how to find the XU limit. Okay, so that was, I think, over here. Yes, okay. How to find XU limit and so on. Okay, we also studied how to find MU limit, right? So this is what we are using it, what we studied above. Okay, right? Fine. So this is how we get this three value. Okay, this is XU limit, this is PT limit, this is MU limit, right? So that this this correspond to this balance section, that is junction, right? After that, if you still increase your PT, then the section becomes overinforced, which is shown in this red line, right? So from the graph we can see that when the section is underenforced, okay, over here you can see the PT limit is 0.96. So above that the section is underenforced, and when you increase the PT limit more than 0.96, then it becomes overinforced, right? So that is this red graph, this is this green graph, this is this junction, right? So in this region, okay, we can see when you increase the PT, okay, that MU also increases, okay? Moment of resistance also increases, and that graph is almost linear, right? But as your section becomes over-enforced, and when you further increase the percentage of steel, but you can see that this, even though you are increasing the percentage of steel, the moment resistance capacity of the section does not increases much, right? That is why under-enforced section are very economical, okay, and over-enforced section they are not economical, right? So that is why there are two drawbacks of over-enforced section. One, that is it undergoes a brittle failure, and second, that it is very uneconomical, right? So this is how this such graphs are very important to understand that why an under-enforced section is more uh, feasible, or you can say uh, economical. Okay, so you can always make such competitive programs, okay, where you can vary the percentage of steel and get the corresponding MUR and corresponding the depth of neutral axis, and you can uh, plot this on a graph, right? Simple, which this is all we have studied. Uh, Once you assume a percentage of steel, let me go back to the under info section, okay. Uh, so this is very easy. This is over info section. This is balance section, under info section, right? So, right. So once you know you have assumed PT, so from PT you can find AST. So AST is known to us, FCK is known to us, B is known to us, F5 is known to us. You can find depth of neutral axis. Once you find the depth of neutral axis, okay, so you can find the uh, uh, the depth at which the force C falls, that is 0.416 XU. Okay, from this you can find XU. Once XU is known, you can find 0.416 XU. Once this is known, you can find Z. C, you know, C is equal to 0.36 FCKB into XU. So C into this lever arm will give you the moment of resistance, right? So that is how you get the moment of resistance in this table, right? So these are the moment of resistance which are found by that formula, that is C into Z, and these are the value of the depth of the neutral axis which we find from the formula for XU which we saw now, right? So The fundamentals for analysis of a rectangular section, that is for slab, okay, is the same as that for beam. Only thing which we have to remember is that in case of slab, we design 1 meter wide strip. That is, we take B equal to 1000 mm, right? I hope you must have found this video useful. Next chapter will be design. Okay, how to design a RC section. Okay, please visit website mmsprogramcivil.com for all the education videos and PDFs. Thank you.